Hey Calypso 900, this is Norbert. So judging from your quiz performance and some of the emails you've been sending to TAs, it seems that quite a few of you are having trouble with understanding the process of doing both one-way and two-way ANOVAs. So I thought it'd be helpful to walk you through an example of each in order to try and clear up some of your confusion. Just as a quick aside, I'm recording this in my dorm room, so please try and ignore any random background noise that you hear. These practice problems and the Excel sheet where I did all of my calculations will be posted on the course website, and hopefully I'll also be able to get them to link in the down bar below. You'll see that when I get into the two-way ANOVA example that I switched from handwritten notes to an Excel sheet because it just got too tedious to keep writing out a lot of repetitive steps. I'll explain my process in this video, and then you can follow along on the Excel file. Also, if you have any questions regarding any of the steps, you can leave a comment below or email the TA account and I'll answer them. Okay, so that's the end of the introductions. Let's jump into our first example. So in problem 1, it says that an experimenter predicts that students will learn best with white noise playing in the background compared to varying sound or silence. She randomly divides 24 students into the 3 conditions. Those in group 1 study with noise at a constant volume in the background. Those in group 2 study with varying sound that changes volume periodically. And those in group 3 study in silence. After studying, all students take a 10-point multiple choice test over the material. Their scores are shown below and assume that the requirements for a one-way ANOVA have been met. So here's the data, and I'm just going to reproduce it in my handwritten notes. So first, in order to get the MS between term, you have to calculate the means for each of the samples. So I've done that here, and you can see that the mean for group A, constant sound, was 6, the mean for random sound was 4, and the mean for no sound was 3.375. And then you also have to calculate the grand mean, which you can either do by averaging the 3 means here, or you can average all of the data in this to get the grand mean, and they should both come out to the same answer. So in order to get the SS of the sample means, since it's a between term, that means it's between the means. So that just means that you do the mean of A, which was 6, and then the deviation from the grand mean squared. Same thing with B, so you have the mean 4 minus 4.46, the grand mean squared, and then likewise for the third, 3.375 minus 4.46 squared. And then you get the SS sample means of 3.76. In order to find the degree of freedom in the between term, you take the number of conditions, so in this case 3, and subtract 1. Therefore you have 2 degrees of freedom between. And then to get S squared sample means, you just do the standard procedure, so it's SS over DF. So we had 3.76 over 2 degrees of freedom equals 1.88. And then to get the mean square between term, you take the S squared of the sample means times n per sample. So in this case, it was 8. 1, 2, 3, 4, 5, 6, 7, 8. 8. So 1.88 times 8 gives you 15.04 as your mean square between term. To get the mean square within term, you have to find sums of square for each condition. So you're going to be comparing the deviation within each of the samples around its own mean. So for the sums of square in condition A, you would do 7 minus 6 squared, 4 minus 6 squared, etc., etc., and then you'll get 34. Same thing with sums of square for condition B. You would do 5 minus condition B's mean, which was 4, so 5 minus 4 squared. Again, 5 minus 4 squared, etc., to get 20. Likewise with condition C, 2 minus the mean for C is 3.375 squared, plus 4 minus 3.375 squared, etc. And then you sum those to get 33.875. And then your sums of squares within will just be the sum of sums of squares condition A, sums of squares B, and sums of squares C. So add the three terms that we just calculated, and you'll get the sums of squares within. In order to get the degrees of freedom within, you've been given the formula k times the quantity n minus 1, where k is the number of conditions. So in this case, we had 3 conditions. And then the n term is the number of observations per condition. Again, we had 8. So 3 times 8 minus 1, so 7, is equal to 21. And then again, to get the mean square within term, you get sums of square within over degrees of freedom within, and that gives you 4.18. Okay, so now we have both our mean square between term and our mean square within term. So then we can do an f-test. So again, we have the values of mean square between, mean squares within, and the appropriate degrees of freedom here. To do your f-test, you do mean squares between over mean squares within, and I calculate that here to be 3.6. So then you look up your f value in the f table with the appropriate degrees of freedom. So in this case, it would be 2 and 21. Just as a side note, when I was looking in your textbook, I didn't see this value. So the more conservative method would be to use degrees of freedom of 2 and 20. But I did some searching online, so I was able to get the exact values for F critical. And in this case, F critical at an alpha of 0.05 was equal to 3.47. And at an alpha of 0.01, the F critical was 5.73. So since we had our observed F of 3.6, that means that we've surpassed the critical value at 0.05, but not for 0.01. So therefore, when we do our reporting, we do it in this format, and we would write F degrees 221 is equal to 3.6. And keep in mind this is the F observed, not the F critical that you looked up in the table. And then you would follow that with P of 0.05, since that's the alpha level that we found our F to be significant at. And just to restate things, your null hypothesis would be that all of the means for for each condition would be equal, and also that the variance between is equal to the variance within. Make sure that you also include this in your hypothesis when we ask for it, because you're going to lose points if you don't include it. It's called an analysis of variance because we are actually looking at variances. And then for the alternative hypothesis, you would say that not all mu's are equal. Sometimes I've seen some people say that mu A is not equal to mu B is not equal to mu C. And while that could be correct sometimes, it's not always correct. For example, in your quiz, I think it was quiz 4, we found that mu A was actually equal to mu B or something like that. So just be careful. It would be a little bit more precise to say that not all the mu's are equal. And then in terms of graphing, I just wanted to show you that this is what the F distribution should look like. And then you have your value of F observed here. And then we saw that it surpassed the F critical over here. So hopefully all of that makes sense for just the process of doing a one-way ANOVA. So another thing that we'd like you to know how to do is to understand how to partition the sums of squares for each term. So I'll be using the same data, but I'm going to just switch over to an Excel sheet because the calculations are a little bit more tedious. So again, this is just reproducing the data set. And then we have the means for condition A was 6, B was 4, and C was 3.37. Grand mean again, 4.46. So now we have to look at what the null model predicts. And the null model predicts that each of the data points in our set can be predicted by the grand mean. So what that means is that in this example we had 24 observations. So therefore each of our 24 observations would be the grand mean. So this is illustrated here, and as you can see, every single value that our null model predicts is the grand mean. And then to find our sums of square total, we base this off of the variation of each data point around the null model. So here I would have the deviation of the observed value of 7 minus 4.46 gives you 2.54, and then continuing on, 4 minus 4.46 is negative 0.46, etc., and you would calculate this for all of them. So these are deviations, and then as a usual procedure, you would do the square deviations. So 2.54 squared equals 6.45. Negative 0.46 would give you this when you square it. And then when you do all of that, for each of the terms, you would add all of the square deviations to get the sums of square total. So in this case, when I added all of these numbers, I would get 117. Now to find the degrees of freedom in the total, you would base it off of the entire data set. So here we had 24 observations, so we subtract 1, and therefore we have 23 degrees of freedom total. Next thing we have to consider is the full model predictions. So the full model predicts that each data point can be predicted by the mean of that condition. So just remember that we had condition A had the mean of 6, and condition B had a mean of 4, and condition C had a mean of 3.375. Therefore, each of the observations that belong to condition A should be predicted by the mean of A. So 6 was the mean of A, and then 6, 6, 6, 6, etc. Same thing for B, mean of 4. All of the observations belonging to condition B should be 4, and likewise with condition C. So our sums of square between terms is based on the variation within each condition around the full model. So what that means is that you have to compare each data point to its respective mean within the condition. So to illustrate that, recall that the mean was mean of A was 6, and the original data that we were given up above in the problem was 7. So the deviation is 1, and then you score that deviation. Same thing, the original data point was 4. Again, the mean of A was 6. You have a deviation of -2. -2 squared is 4, etc., etc. And then, as our usual procedure, we would sum all of our square deviations. And when I do that, I get the sums of square for within A. Same procedure for B. You would do the original B data minus the mean of B to get the deviation. Then you square the deviation. Do that over and over. Sum the square deviations, and then you'll get the sums of squares for B, and the exact same thing for C. So to get your total sums of squares within, you would do the sums of squares of A that you found, sums of squares of B, and sums of squares of C. And when you add these numbers, you'll get sums of squares within here. So I calculated that to be 87.875. So next, in order to find your degrees of freedom, remember that your degrees of freedom is based on each sample times the number of samples. So your degrees of freedom would be the degrees of freedom that you have for A, plus the degrees of freedom for B, plus the degrees of freedom for C. So we calculated all of this based on the individual conditions. So in condition A, we had 8 observations, so therefore we had 7 degrees of freedom. Again, for B, 8 observations minus 1 would be 7, and likewise for C. So that means in total you would have 21 degrees of freedom for degrees of freedom within. And moving on, the sums of squares between term is based on the variation from the full model predictions. So to say it another way, that's how much the full model varies around the grand mean. So again, we had the full model predictions here. So every observation within A should be at the mean of A, so 6. Same for B. Every observation should be at the mean of B, so 4. And likewise for C. So then we would try to find the deviations of these model predictions from the grand mean. So here I calculated 6 minus 4.46 is equal to 1.54, and then notice that it's the same calculation over and over for everything in the condition. And then same thing we do for B. You have 4 minus 4.46 with a deviation of negative 0.46, and do that the same way for everything in B, and likewise for C. 3.375 minus 4.46 equals negative 1.085, and do that for everything in that column. And then we square the deviations, as we usually do. So 1.54 squared is equal to 2.3716, and copy that all the way down. Negative 0.46 squared would be 0.2116, and copy that down. And then for C, minus 1.085 squared would be 1.17 and change, and copy that down. So then when we're done with that, we would get the all of these square deviations, and then we would take the sum of the square deviations. So add all of these terms to get the SS between, and I calculated that to be 30.08 and change. And then to find the degrees of freedom, between is based on the means varying from each other. So in that case, the degrees of freedom between is equal to the number of conditions minus 1. So just remember that it's between the means. So since we had 3 means, or 3 conditions, it's 3 minus 1 equals 2 degrees of freedom. And then now we're just going to summarize our work in one of these tables. And so we have the sources of the variation, so within and between, then the sums of squares that we calculate for each of them, the degrees of freedom that we calculated, and then to find the mean squares, having everything in this table form is very helpful because all you have to do is divide across the row. So 87.875 divided by 21 gives you the mean square within term here, so 4.18. Likewise with the between, SS between over DF between gives you MS between. And then recall that when we want to do our F test, we would do mean square between over mean squares within. So just divide through this column, and you would do between minus between over within, and then that's how you get that value. So next, I just like to do a quick example of how to do some pairwise comparisons with the same data. So I'm just going to open up this tab, and I'll just give the essential information. So remember that we had the means A, B, and C, so 6 for A, 4 for B, and 3.375 for C. And then this is just reproducing the work that we had on the previous tab. So this would be an example of an LSD. And I just chose to do an LSD because it's the simplest. The only difference between an LSD and a Tukey HSD is that in Tukey's HSD, you just have to find a penalty term. So it would just be based on the degrees of freedom within the groups that you have, and also the number of means that you're comparing. And you can just find those values in one of the tables that we'll give you. So if you have any questions about doing a Tukey's HSD post hoc pairwise comparison, you could just ask me and I'll try to clarify it. But I think an LSD example would be just as equally illustrative of how to do this. So first you would have to find the standard error of the difference. And we give you this formula, and it's the square root of 2 times the mean square within term over n per condition. So that's just 2 times the mean square within was 4.18 over n per condition. So we had 8 observations per condition, square root that whole thing, and then you get the standard error of the difference. And I calculated that to be 1.93 and change. And then you use this standard error of the difference term as the denominator in all of your pairwise comparisons. And basically, when you're doing your pairwise comparisons, all you're doing are t-tests. And it's just a standard procedure that you do when we did t-tests before. So for example, if we wanted to do a pairwise comparison between condition A and condition B, we take the mean of A, 6, minus the mean of B, which is 4, and then all of that over the standard error of the difference, 1.94. And then that gives you a t observed of 1.03. And then I just happened to look that up in a t-table. So remember how I report a t-test result, t, and then the degrees of freedom that we have. And then remember, this is degrees of freedom within, okay, 21, is equal to the observed t, and then the significance value. So when I looked it up in a table, it was less than 0.4, which is not very significant, I guess. And then it's the same procedure for comparing the means of A and C. We have the mean of A minus the mean of C all over the standard error of the difference, and that would give you this number as your t observed. And again, you report it. And likewise for a pairwise comparison with B versus C. So mean of B minus the mean of C all over the standard error of the difference. And then that's the value I got. And this one was actually not tabled because our table only goes up to 0.5, so it had to be greater than 0.5. And yeah, just a reminder, you're always using the degrees of freedom within. So in this case, it was 21. And that's how you do pairwise comparisons. So I think I'm going to move on to our second example, which is a two-way ANOVA. Okay, so let me close this. And so here's our second problem. It says that a research study was conducted to examine the impact of listening to different types of music on adults' and children's performance during a memory task. Half of the students received a classical music, and half were given pop music. All of the participants, both adults and children, were given a memory test with higher scores representing better performance. And the data for the test scores are produced below, and just assume that the requirements for the two-way ANOVA have been met. So here we have two factors with 2 levels each, and I believe the way that Professor Wright notates it, the columns would be your factor A, and then the rows would be factor A, and the columns would be factor B. So one factor would be, I guess, age with 2 levels, adults and children. And then your second factor would be type of music with 2 levels, classical music and pop music. And then this is just the data. So I'm going to reproduce that in the Excel sheet. And because it's kind of hard to contain, I guess, all of these things in the proper cells, I've tried to color code them. So it's just that the red boxes will be corresponding to this cell, the yellow would correspond to this cell, the blue will always correspond to this cell, and the green will always correspond to that cell. So here we have the original data, and then I would take the means for each of the cells. So for the red cell, when I average all of these numbers, I would get 8, and then average all of the things in the blue cell, and I'll get 4. Then average all the things in the yellow cell to get 5, and then average all of the things in the green cell to get 3. And then after we have the cell means, we would calculate the marginals. So in order to calculate the marginals, you just average across rows and down columns. So in this case, 8 plus 5 over 2, 6.5. Same thing, 4 plus 3 over 2, 3.5. And then to get the marginals of the columns, you would do 8 plus 4 over 2 gives you 6, and 5 plus 3 over 2 gives you 4. And then after that, you can calculate the grand mean in a couple of ways. So you can either average all of these cells, and then that would give you the grand mean, or you can also average the column marginals or the row marginals, and it should give you the same answer. So now we have to partition the sums of square terms. So the sums of square total terms are the deviations of each observation from the grand mean. So I'm just going to scroll up really quickly, and then what this means is that we did the deviations are 10 minus the grand mean of 5 gives you 5, 7 minus the grand mean of 5 gives you 2, and then you do the same thing and you find the deviations for all of the observations, and then these are the deviations that I got. And then after that, you would square all of the deviations. So we calculate the deviations here, and then we square them. So 5 squared is 25, 2 squared is 4, 4 squared is 16, etc., etc. And then we sum all of the square deviations to get the sums of squares total. So when you sum all of these square deviations, you get 106. The next term that we're interested in is the sums of squares within. And the sums of square within term is based on the variation within each cell around its own mean. So I'm just reproducing the cell means that we had above. And this is the original data here. So to calculate the within deviations, we would do 10 minus 8 gives you 2. 7 minus 8 is negative 1. And then you do the same for everything in this cell. And then likewise, you would do the same for B, but this time you would be comparing it to the cell mean for B. So you would be doing 5 minus 4 is equal to 1. 4 minus 4 is 0. And do the same thing for everything in the blue cell. And then for the yellow cell, compare all of the original data in this cell to its own mean. So again, 5 minus 5 is 0. 4 minus 5 is negative 1. And do the same for everything else in the yellow cell. And then for the green cell, it would be 3 minus 3 is 0. 4 minus 3 is 1. And do the rest for the green cell. And that gives you the deviations. and then again, we would square the deviations. So 2 squared is 4, 1 squared is 1, etc., etc. And then same thing for the blue cell would be 1 squared is 1, 0 squared is 0, and same thing for the yellow cell would be 0 squared is 0, -1 squared is 1, and same thing for the green cell. So 0 squared is 0, 1 squared is 1, etc., etc. And then you have all of these square deviations. So to get SS within, all you have to do is sum all of these numbers. And when I sum these, I get 36. The following term that we're interested in is the sums of square between overall. And the overall term is based on each cell means deviation from the grand mean, and also the number per cell. And the number per cell will come in at the end when we just have to multiply by the number per cell. So again, I'm just reproducing here the cell means. And then since we're interested in each cell means deviation from the grand mean, we would do 8 minus 5, the grand mean, gives you 3. 4 minus 5 is -1. 5 minus 5 is 0. And 3 minus 5 is -2. Then we would square these deviations that we found. And then so 3 squared is 9. -1 squared is 1. 0 squared is 0. And -2 squared is 4. So then, to calculate the sums of square between overall, we would sum all of these square deviations that we just calculated. So that would be 14. And then we would multiply that by the number of observations per cell. So in this case, it was 5. So 14 times 5 gives you 70. And 70 is your sums of square between overall term. But notice that we called this sums of square between overall. So we can actually partition this into each factor. So we can get also SS within A and, or I'm sorry, SS between A and SS between B. So to get that, we would base our sums of square term on the marginals. So in this case, we had the marginal of 6.5 for A, and subtract the grand mean was 5, and that gives you 1.5. And then likewise, we had another marginal of 3.5 minus 5 was the grand mean, and then that gave us 1.5. So then we squared the deviations that we just found. So 1.5 squared is 2.25, and same thing here. So then we would sum the squared deviations that we just found. So 2.25 plus 2.25 gives you 4.5, and then we would multiply that by the number of observations we had in that factor. So for factor A, that would be, I believe Professor Wright said yeah, so factor A would be your rows here. So you had 2 marginals here. And going back to where we were, you have 10 observations total in a single row. And then to get the deviations for the B marginals, you would do the same thing that we did for the A marginals. So we had the marginals 6 and 4. So the marginal 6 minus the grand mean of 5 gives you 1. And then the other marginal that we calculated was 4 minus the grand mean 5 gives you 1. Then we square the deviations. And so 1 squared is 1. And then the other 1 squared is 1. And then you add those square deviations here, 2 times the n per column. So in this case, we had 10 observations per column. So 2 times 10 gives you 20. So that gives you your sums of square between A term, which we calculated to be 45, and then the sums of square between B term to be 20. The last thing that we can partition sums of square between overall into is the interaction term. And then now we know that the interaction term is based on the variability in the cell means not predicted by the additive combination of main effects. So what does that really mean, the additive combination of main effects? So first we would have to calculate the effect, and the effect is calculated by comparing the marginals to the grand mean. And then we would say that the predicted cell values are based off of the effects of being in each row and column compared to the grand mean. So let me step you through what all of this means. So recall that we had these marginals. So we have 6.5, 3.5 for factor A, and then 6 and 4 for factor B, and the grand mean 5. So what that means to calculate your effect would be this marginal 6 minus the grand mean 5 gives you 1. Same thing with the marginal mean for B1 and A2, or I'm sorry, the second column of B, and that would be 4 minus 5 is negative 1. And we do the same thing over here for the row marginals. So 6.5 minus 5 gives you 1.5, or I'm sorry, positive 1.5. And then 3.5 minus 5 gives you negative 1.5. And then also note that the effects for your columns should cancel out. So 1 minus 1 gives you 0. And same thing for the effects for your rows. So 1.5 minus 1.5 equals 0. So next, the way we do this whole additive combination thing is that we would take the grand mean that we have, and then based on the effects that we just calculated, we would try to get the predicted cell mean. So to illustrate this, we have the grand mean of 5 here, and then because it's in this row and this column, we would say, okay, the effect of being in this row is 1, is to add 1, and then the effect of being in this row is to add 1.5. So 5 plus 1 plus 1.5 gives you a 7.5 as your predicted cell mean based on the additive combination. So we do the same thing for each of the cells. So here, grand mean of 5, and then since we're in this cell now, we take this effect is 1, and then minus 1.5 gives you a predicted cell mean of 4.5. And same thing here, grand mean of 5. And then since we're in this cell, which is in this row, so we would add 1.5, and since we're in this column, minus 1. So 5 minus 1 plus 1.5 gives you a predicted cell mean of 5.5 based on the additive combination. And same thing for being in this cell. So 5 minus 1 minus 1.5 gives you 2.5. So to sum all of that and put it in one place, our additive model predictions are that the cell mean should be 7.5 for the red cell, 4.5 for the blue cell, 5.5 for the yellow cell, and 2.5 for the green cell. And these are the predictions based on the additive model for the cell means. But remember that earlier we calculated observed cell means based on the actual data that we have. So I'm just reproducing that here. And then our observed cell means were 8 for the red cell, 4 for the blue cell, 5 for the yellow cell, and 3 for the green cell. So the next thing that we have to do is find the deviations of the observed cell means from the predicted cell means. So to do that, we do observed 8 minus the predicted 7.5 gives you 0.5. Observed value of 4 minus a predicted value of 4.5 gives you negative 0.5. And then same thing here, observed 5 minus predicted 5.5 gives you negative 0.5. And lastly, observed of 3 minus the predicted 2.5 gives you 0.5. So these are the deviations of the observed cell means from the predicted cell means. And then the next thing we do, as always, is we square the deviations that we just found. So 0.5 squared is 0.25, and negative 0.5 squared is 0.25, 0.25, and same thing for the yellow cell and the green cell. And then all we have to do to get this is to sum all of these, right? So that's, when we sum all of that, it's 1 times 5, which is the n per cell. So remember that each cell that we had in the original data set had 5 terms. So 1 times 5 gives you 5. And then with that, now you have all of the sums of squares terms. So the next thing that we have to worry about is finding the degrees of freedom. So remember that we found sums of squares between overall based on each cell's deviation from the grand mean. So since we had 4 cells total, so 2 rows and 2 columns, we have 4 minus 1 equals 3 degrees of freedom for between overall. And then since we know that the sums of square between a term came from factor A's marginals deviation from the grand mean, we had 2 marginals for factor A, so 2 minus 1 gives you 1. And likewise for sums of square between B, you had two marginals for factor b. So 2 minus 1 gives you 1. And then remember that the sum of the square a by b interaction term came from the deviations of the observed means from the predictive means from the additive model. So, therefore, you must have had the marginal means to obtain the predicted values needed to generate the additive model. Also, you must have the predicted values in order to get the deviations from the predicted values. Therefore, you know that the marginals have to be fixed. And then once you know the one cell mean, you have to know the rest based on the marginals. Sorry for the typo. Therefore, in the 2 by 2 ANOVA, you would have 1 degree of freedom for the interaction. Lastly, the sums of scores within term came from the variation of each cell around its own cell mean. So, since we had total of 20 total observations and 4 total cells, we lose 1 degree of freedom per cell because we're calculating everything based off of 4 cell means. So 20 observations minus the number of cell means we have, so minus 4, gives you 16. And then to get the degrees of free total, you just add up all of the degrees of freedom that we just calculated here. So to summarize in our pretty little table, we found that SS between overall was 70 with 3 degrees of freedom. SS between A had sums of square of 20, degrees of freedom 1, and you can see the rest here. And then, like I said, having everything in table form makes it really easy to find the mean square term. Typically, we don't calculate the means. The mean square between overall term. So we would only calculate based on each factor. So to get sums of square between to get mean square between A, 20 divided by 1 gives you 20. For mean square between B, you would do 45 divided by 1 gives you 45. And then to get the mean square for the interaction term, you would do 5 divided by 1 gives you 5. And then for mean square within, you would do 36 divided by 16, and that gives you 2.25. And then again, you would do the f-test. So remember that's ms between over ms within. So we would do ms for A, so that's 20 over ms within is 2.25, so 20 over 2.25 gives you the f value observed for A, and then do the same thing for B, so 45 over 2.25 gives you 20, and then you have 5 over 2.25 gives you 2.2 repeating, and that's for the interaction term. So these will give you your F observed values, and then you have to look at the F criticals in your table. So I looked them up for you, and then I found that F critical with 1 degree of freedom in the numerator and 16 in the denominator at alpha equals 0.05 gave you F critical of 4.49. And then for alpha at 0.01, F critical is 8.53. So then we would fill in the rest of our summary table. And based on this, we see that this F value has exceeded the alpha 0.01 level. So 8.88 is greater than 8.53. So your significance is less than 0.01. Same thing here. You see that you have F equals 20 and you've surpassed F critical at the 0.01 level, and that gives you P is less than 0.01. But notice that this interaction term that we calculated, the F test does not yield a significant result. So we have an F observed of 2.22, but at 0.05, we need an F critical of 4.49. So therefore, P is greater than 0.05 and is not significant. And just to wrap things up, we have to report it in the correct format. So again, F and then the degrees of freedom between, degrees of freedom within, equals the F observed and the significance level that you found. So since we said that condition A was age, we would say that there was a main effect for age and then the typical reporting format. And then likewise, we found that factor B was significant. So we would state that there was a main effect for the music type and then the typical reporting format. And lastly, we found that there was no significant interaction term. So we would say that there was no significant interaction between age and music type and just the normal reporting convention here. And I think that's it for the two-way ANOVA. I hope this helped, guys. And if you have any questions, just email us or you can leave a comment in the comments below. So yeah.